Okay, so we have Shen to present his paper, Efficient System Call Interception for ARM. Yeah, feel free to start.
Thank you. Thank you for your introduction. And good morning, everyone. I'm Yang Shen from National University of Defense Technology. Today, I will present ASC-Hook, an efficient system call interception for ARM. Here is the outline of today's talk. First, I will cover the background, then introduce our ASC-Hook design, present the experimental result, and finally discussing the elimination and the conclusion. Let's begin with the background. Intercepting this call has various applications such as program chasing and debugging, improve reliability and security, emulating different operating systems, but still face inefficiency in ARM. Recently, Yatsuda et al. Proposed a new method for x86 called the trampoline. As illustrated in this figure, the RAS register holds the physical number. The trampoline replaces physical instruction with a 2-byte call queue star RAS register instruction along the program to jump to the virtual address between 0 and the maximum physical number. A trampoline is placed at the address 0, so when execution reaches that entrance, it jumps into the trampoline routine. This design guarantees an efficient syscall with a minimized overhead in x86. However, this approach faces challenge on ARM platform. The first challenge is that the ARM architecture requires instruction to be 4-bit aligned. If a similar instruction to call queue star RAS directly used on x86 is directly used, it may jump to a long-aligned address and resulting in a bus error. The second challenge concerns returning to the original control flow after the jump. ARM don't have an instruction like call queue and can jump and push the return address onto the stack. Using a BL instruction, batch and link would overwrite the important S30 register, which store the return address of the last function call and is clearly unacceptable. Now, so therefore, our work focus on overcoming this challenge to enable efficient system call interception on ARM. Now let's move into the method section. To solve this challenge, we have two key observations. First, the total number of SVC instructions with a processing memory image is very limited, especially for high-level language users who typically rely on the second system call for shared library rather than writing SVC instruction directly. Table 1 shows that the number of SVC instructions in the process image of the sum of the applications, with most have fewer than 1,000. Second, for most system calls, at least 2 instructions can be replaced. Based on the ARM architecture, the system call number must be passed to the S8 register before inserting the SVC instructions. Therefore, we can at least replace the SVC instruction and the instruction that assign the view to the S8 register. Table 2 shows for each application how many SVCs are actually used and how many of them cannot be intercepted by our 2 instruction replace method. Only Negas and Apache has such remain SVCs, which further validate our observations. For that one remain SVC in Negas and Apache, we fall back to signal-based interception. The signal-based interception works by using BRK or illegal instruction to replace SVC, which allows a signal trip or signal yields, respectively, allowing us to catch the system call while signal handlers. However, it requires a frequent user model to kernel mode transactions and thus incurs significant overhead. We therefore use this approach to only as a fallback method. Based on the observation above, we devised our replacement strategy and the trampoline design. This figure gives an overview of ASC-hooks. Our approach targets each SVC instruction and its preceding move S8 physical number of operation for replacement. Our replacement strategy includes 2 methods. First, we use the move instruction to load the address of the first level trampoline near the designation register S8 and replace SVC instruction with the BR instructions. This method is limited by the constraint of the move instructions, which accept only a 16-bit immediate view. Consequently, The reachable virtual address range is limited to the range from 0 to the 65,535, coordinating a total number of 6,383 instructions. According to our trampoline design, each first-level trampoline requires 4 instructions, allowing for up to 3,840 trampolines. However, as previously observed, the number of SVC instructions in typical application is very limited, making it almost impossible to reach this limit. This method currently serves our primary replacement approach. Second, we use ADRP instruction to load the target address into the destination register S8. Again, replace SVC instruction with the BR instruction. Since the ADRP produces a page-aligned address, trampoline multiplays at the beginning of the memory pages lead to significant overhead. Therefore, we use this method only when the first method reaches the limit. Although we have not yet encountered application that requires this fallback, it retains as a precautions. This design guarantees a 4-bit aligned jump and avoid the issue of misaligned jump address. Our trampoline mechanism addresses 2 key challenges. The first challenge is restoring the original instruction flow after incepting a physical. Using BLR to jump with overwriting the S30 register, directly push the return address onto the stack without replacing additional instruction, which is not feasible. Our solution is to design a dedicated trampoline for each SVC that pushes the address of the instruction following the SVC onto the stack. Then this allows us to retrieve the return address from the stack after inserting the SVC in the trampoline. The second challenge is limited immediate view range of the move instruction, which is restricted to 60 bits. This limits the directly jumpable virtual address range from 0 to the 65,535, make effectual use this narrow range critical. To overcome this, we design a multi-level trampoline scheme. We implement a 3-level trampoline hierarchy. The first and the second level are dedicated to each SVCs, while the third level is shared across all system calls. Level 1, a 4-instruction sequence that quickly redirect execution will minimize address space usage. Level 2, trampoline first re-executed the previously replaced assignment instruction to restore the original views of the S8. Then it pushed the return address, ES, the instruction following the SVC, onto the stack and transfer control to the third level trampoline. Level 3, upon entering the trampoline, the register content is first saved. Next, the user provides hook function is called. After that, the register state is restored, the original control system call is executed. The return address is popped from the stack to resume execution at the original instruction flows. This multi-stage trampoline design effectively solved both return address preservation and limited jump range challenge. However, if jump target fall between the two replaced instructions, the first instruction, which assigns the first level trampoline to address to S8, may be skipped. This results in an incorrect jump target. To handle such edge cases, we fall back to replace such SVC instruction with a BRK or illegal instruction to intercept through signals. We propose 3 methods to identify such cases. First, if no assignment to S8 register is found preceding the SVC instruction, we intercept this SVC using signals. Second, for directly jump instruction, we inspect all directly jump instructions in the process memories and calculate the target address. If the jump address falls between the 2 instructions, we switch to signal-based handling for corresponding SVCs. Third, for directly jumps, if the jump target falls between the 2 replaced instructions, only the BRS8 is executed. Since the S8 contains the signal number, this inevitably triggers a segment fault or bus error. With the signal handler, we perform further analysis. The PC views equals the S8, which is equal the signal number, and the S8 certainly contains the return address. Using this information, we can infer the signal number and also recover the address of the original SVC instruction. We are appending this data to a configuration file for further use. These methods are rarely triggered in practice. The main purpose of this method is just for insurance. Now let's dive into experiments. Our experiment was performed on ARM platform. The configuration is shown in the slide. We compare ASC-Hook with p-trace, signal interception method, and LD plot. First, we measure the overhead of intercepting a single signal system call using gate PID as the test cases. To eliminate the kernel cross system call overhead, we use the hook function that returns virtual views. Shown in table 3, LD plot has lowest overhead. ASC-Hook incurs about 5 times of LD plot, while signal interception and p-trace are 29 times and 61 times of the ASC-Hook respectively. To evaluate the overall runtime impact of ASC-Hook, we select SQLite, use its speed test 1 benchmark, and MPI-BFS. MPI-BFS is our own implementation of the branch-first search algorithm using MPI and be open sourced together with the rest of the project code. As the figure 3 shows, ASC-Hook is just 0.3 seconds of the overhead, only 3.3% of the SQLite speed test 1 runtime, total runtime, while for BFS, its overhead is merely 0.3% of the overall execution times. We select Redis, Apache, interval or random, Iowa, and Negas as a benchmark program to elevate the impact of ASC-Hook on application throughput to minimize the impact of inter-host communication. We select both client and server on the same machine. For Redis, we use its built-in benchmark tools. For Apache and Negas, we employ WRK to generate HTTP workloads. As shown in figure 5, the throughput degradation caused by ASC-Hook is significantly lower than other two methods within the performance drop of 0.96%, 1.77%, 4.98%, 9.94%, and 4.8% for application listed in order. To investigate the impact of the signal transfer size on performance degradation in failed IOs and the network throughput, we conduct further tests on read bandwidth of IOR and Negas throughput. For IOR, we adjust the single transfer size. For Negas, we change the size of the return static resource fields. The results show that for IOR, a single transfer size increased, bandwidth steadily improved, approaching the diverse bandwidth limit, while the performance degradation caused by signal call interception tools gradually deceased. For example, ASC-Hook's overhead dropped from 9.94% at 1 kilobyte to 1.97% at 64 kilobyte, mainly because the proportion of the system call overhead with the entire I/O stack decreased as the transfer size increased. For Negas, a similar pattern is observed. ASC-Hook's performance degradation dropped from 4.8% at 0 kilobyte to 1.4% of 1 megabyte, while p-trace drops from 35.3% to 21.8%. Furthermore, compared to other two methods, ASC-Hook consequently exhibited low overhead across in all fail sites. The next up is part 4, conclusions and limits. Limitations of the ASC-Hooks. Due to our first replacement strategies requirement for low virtual address, ASC-Hook is not supported on Windows or Mac OS. On the both platforms, virtual address location is either restricted or fails by default. However, we can completely avoid using the first replacement strategy, and instead on the second replace strategy, it may solve this issue by resulting in a significant memory overhead. ASC-Hook use LD plot to replace SVC instruction before application startup. Any SVCs in the library load later, for example, while still open, will not be hooked. We can address this issue by adapting the online binary rewrite approach proposed in S containers. Since our tools register signal handler before application startup, they may be overwritten by the application's own handlers. However, even without using signal for interception, our first two method strategy can meet the need of the most applications. Moreover, most applications at least do not intercept signal generated by debugging instructions. The virtual dynamic share object enables user space program to access certain syscodes directly by expose their implementation through the kernel. ASC-Hook don't support hooking VDSO-based system calls. However, we can disable VDSO to address this issue. In edge cases, ASC-Hook may encounter some performance bottlenecks. For example, if the total number of SVC for a process is exceeding the 3,840, or if the BRK or illegal instructions are repeatedly executed, the overhead could become significant. However, as shown in the table 2 and the evaluations, there are extreme cases and rarely occur in practice. In conclusion, we present ASC-Hook, a system call hooking mechanism for ARM. It ensures efficient and comprehensive interception through a novel urban design. We intensively test ASC-Hook with real-world application, demonstrate its comprehensive and efficient interception capability. The experiment results indicate that ASC-Hook maintains an average performance overhead of 3.8% for most system call intensive application. Our implementation is open source and available at the link shown on the slide. Let's conclude my talk. Thanks for your listening.
Thank you. Any questions?
So you have shown an overhead with the LD preload variant, at least on one of your benchmarks, right?
Yes, because...
Could you explain what you do exactly? Because I don't think LD preload allows you to change the instruction, just to override functions.
Pardon?
So when you use LD preload as one of your comparison base, right?
Yes.
What exactly do you do to intercept the system call at that level?
Please wait a minute. LD preload is I chose LD preload because it is a symbol of the function method to intercept the system calls, and the character of this method is very fast, but it very hard to hook all of the system calls, and so it's very difficult to employ it. It takes a lot of work to employ it to all of the application we test. And we think that although it is efficient, but it can't cover all the system calls, because the system calls may appear out of the function, or in a function it will appear multiple SVCs, and whether it can do intercept all of the system calls with its function in practice, I really wonder if it is possible in the practice.
Okay, thank you.
Great, thank you. Any questions? More questions? No? Okay. So I have a quick one. So what are the key challenges compared with the x86 paper, the trampoline? In 2023.
2023?
Yes. So assume that there's a bunch of banner translation tools available, and the x86 they have done this interception with very high performance. So what are the key challenges for doing this on ARM?
First, the ARM architecture. Although we first introduced the trampoline, and here's a very beautiful work, interception, the system calls in the LCTES'25. But he has, according to his method, it will has two challenges. First, if we use the CoQ star AS to jump to the virtual address, because ARM's instructions must be to address to 4-bit aligned. If we directly jump to the use his method, the physical numbers will not always multiply of the 4, so it will cause a bus error. And the second challenge is restoring the return the original control flow after the exception pin. The x86 can push the address. The CoQ instruction can push the address of the system calls, but But in ARM, it don't have such a function calls instructions. The BL instruction will overwrite S30 register, which store the last function call's return address, and it will ruin it. So it is not feasible.
Okay, thanks. I think join me to thank Yang again, and let us move to the next speaker.